Okay, hello everyone. This is a continuum emission across Geospace session. This is a mix between the GEM focus group on mesoscale and the CEDAR community. For those of you that, I don't see anyone, but I'm going to say it probably throughout, this is a giant room and we want to have discussion. So don't sit in the back, we won't see you. Come forward. The creation of this session is actually a continuation of the Steve session that we all love and like. So for the students in the room, I just have 2 slides. What is Steve? Steve stands for Strong Thermal Emission Velocity Enhancement, and that is thanks to Bob Lysak during the 2016 AGU meeting in Eric Donovan's presentation, where we knew Steve was a name, but looking at the characteristics, Bob Lysak just said, what about this? And that's how the name occurred. In 2016, this was a new aeronomical phenomena. It was discovered by citizen scientists, and it is observed, as you can see here, as a mauve arc that propagates westward. So in this case, westward is going to be towards us. And it's sometimes observed with these green finger-like structures that we call the picket fence. Some exciting things about Steve that you probably have seen is that they're associated with subaraural ion drift. And this is the first time, to my knowledge at least, that we have an optical association of an SAID. But it's not any SAID. It's an extreme SAID. As you can see in the plot below, those are data from Swarm satellite. And I'm sure that some of the speakers will tell you some of that story. Very interesting, although this is an emission in the night sky, this is not produced by particle precipitation. And we have seen that via satellite, but more importantly maybe is when we look at the emission in the spectrograph data, this is a continuum emission. And this is where the session comes, like how these continuum emissions are produced in the ionosphere. And the story that you are going to see throughout this session is that this is not only observed for Steve. We are seeing this type of emissions not only in the subaraural region, but in other regions too. And we need to understand first, are they all produced in the same way? Are they all linked? Do we see the same characteristics? So this is definitely a new and important topic. So to me, Steve is the perfect GEM CEDAR joint attendee because it is an excellent example of MIT coupling. So Steve was very happy about this joint meeting happening. The discussion is not going to stop here because many of you know that Phil Erickson organizes every year, or anytime we can, what is called the Steve Workshop. And this year, we're going to have the Steve Workshop on October 16 to 18 in Fairbanks, Alaska. So besides the amazing team that always organizes the meeting, we also have an amazing local organizing committee that you probably can recognize Vincent as part of it. And Don Hampton and Marcon, they have been fantastic hosts. So it's going to be very, very good to continue the discussion that we are starting today. Very, very quick, the workshop is designed in discussion. So there are almost no talk, and that's what inspired this session. Let's have the talks, let's have the discussion. We don't want the very polished talks, interrupt, ask a question. So there are very few talks today, but the idea is to start a conversation with the community. And we have additional activity plans for the meeting, so if you're interested in participating and doing something that is Steve-related or continuum emission-related, talk to us. And that's all the introduction, so we can move to Vincent. All yours.
Cool.
I'll give you the mic.
Sounds good. All right. Hello, everyone. My name is Vincent Ledvina. I'm a PhD student at the University of Alaska Fairbanks, and I'm going to be covering an event that we saw earlier in January this year up in Fairbanks. And actually, the story of how we noticed this event is that I was on the plane going to Fairbanks, and I just checked the all-sky camera at Poker Flat all the time, and I noticed this really weird thing happening. So as I was taking off, I was just trying to screenshot everything that I could. And then when I got to Fairbanks, just sat down and realized how crazy this thing was. So here's the outline of what I'll be talking about, and there's the event right there, right at the zenith of the Poker Flat all-sky imager. I'll first give you a little bit of introduction on continuum, aurora, sort of emissions, and then also these things called fragmented aurora-like emissions. I'll go over the event, some key features, then just run through some data. This is just sort of presenting the event. We don't necessarily have any concrete conclusions yet, because this just happened. And then hopefully, in the last slide, I have some questions that will spur discussion. So Bea already went over a lot of this about the continuum emissions, so I'll actually just focus on the fragmented aurora-like emissions, which are sort of these green blobby features that mostly appear poleward of the auroral oval, so usually in Svalbard, but they look very similar to the streaks underneath the picket fence of Steve. So you can see there at the bottom right, there's Steve, and then you see the label, and then the picket fence, and then right underneath, it's kind of like a messy exclamation point. It's not field aligned. It's this little thing kind of sticking out perpendicular to the picket fence. Those look very similar to these things called fragmented aurora-like emissions. There are multiple types of fragmented aurora-like emissions, type 1 and type 2, referring to whether they're in groups or they're individual. They're not field aligned, as I said. They could be created by some sort of local process like parallel electric fields. There's been some research looking at that into the generation mechanism of Steve's picket fence. And they're not the same as auroral beads, which is what I'm most familiar with. But I thought I would mention that because they don't explosively brighten like beads do. They're very small like beads, however, so people often confuse them with auroral beads. So here's the event that we're looking at today. It happened right overhead in Fairbanks, Alaska, and it was on January 4th, 2025 from around 1630 to 1700 UT, so local time, that's almost 8 a.m. So because this was near the solstice in Fairbanks, we get a really long range of dark hours, so it stays dark and we can see aurora all the way up to 8 or 9 a.m. And you can see, I'll just play this again. Oh, it's playing automatically, great. So here's the all-sky camera from Poker Flat. You can see the cardinal directions labeled, north, south, east, and west. There's sort of this active aurora, and then you can see these fragmented aurora-like emissions just streaming along, propagating eastward, and this is all sort of poleward of some patchy, diffuse aurora going on, and then there's the continuum aurora, which is that sort of white blob that forms right overhead at the zenith of the imager, and this is all occurring during active geomagnetic conditions, and I have some plots about that. And this is just freezing some frames, sort of going through the different things that we're seeing. So we have the type 1 fragmented aurora-like emissions, which are just like these single blobs. And then we have sort of these type 2, potentially, FAEs, which are in groups. Sometimes those type 2 FAEs, strangely enough, can appear field aligned. And then we have this continuum emission right overhead. And I have the question mark there, but Don Hampton, who's my advisor, is on a raft somewhere in the Brooks Range in Alaska right now, but he did send me an email earlier this week, over the weekend, that looking at the spectrograph data, it is a continuum. So no need to have the question mark there. And here's where we have availability of imagery. We have Poker Flat, which is down here, right near Fairbanks, and we also have Toolik Lake, which saw the FAEs but not the continuum, which happened too far south. But there's a possibility to triangulate some of these FAEs since we have them in both imagers, which is pretty cool. Here's the solar wind at the time. Nothing really too important to note here other than that we were in a high-speed stream, and the BZ was negative for over 2 hours before the event took place. So here's just kind of looking at roughly a day and then sort of overall the context going on, so high-speed stream. And looking at ground magnetometers, at the bottom here is the SIM-H, so that's basically the DST. And it actually occurred during a slightly active time, so I think on here you can see it's like -80 or so, which is fairly active. And it was in the broader range of active geomagnetic conditions. There was actually a severe geomagnetic storm over the New Year, so I think things were sort of just calming down from that. And then looking at the supermag indices, there was a substorm that occurred right after the event. So you can see this large negative bay, and then if you actually go to the Poker Flat ground magnetometer, you can see the same thing. And this is AE up here, which just shows that over the sort of 2 days surrounding the event, there was a lot of stuff going on. What's probably the coolest thing to look at, though, is the context of the images, which are up here with different timestamps, and the Pfizer measurements. This is the poker flat incoherent scatter radar. These plots are courtesy of Toshi Nishimura, so I'm not a Pfizer person at all. In fact, I tried downloading the Pfizer data and I couldn't figure it out. So if you have really specific questions about Pfizer, I urge you to contact Toshi. But what I can tell you is that we see in the field-aligned beam, which is this left panel here, this probably represents data right near the continuum emission, which was right sort of at the zenith of the imager. And we can see enhanced ion temperature, which may be indicative of strong frictional heating. So like Bea said, these continuum emissions are not really produced by particle precipitation. And then when you're looking at the northward beam, which is in the middle here, this density drops around 1650 UT. And up here, these circular images, these are the all-sky camera images, and there's different time steps going from 1640 to 1710 in 5-minute increments. And just so that you're all aware, the location of this incoherent scatter radar is basically at the center of all these images here. And so you're seeing a density dropout, and then it increased later. And then here we're looking at the line of sight velocity from the beams, and there's maybe a small line of sight velocity. So that means that the flow is eastward, and we can kind of, confirm that because all these fragmented aurora-like emissions and the aurora in general is flowing to the east. And there's really no clear trend in the field-aligned velocity overall. And then I also had, my roommate was actually awake at the time at 8 a.m. because she's an aurora guide. So I texted her right before the plane took off. I said, hey, you should go out and take some video of this thing happening. So she was like out of the shower, about ready to go to bed. But she went out there with her camera, which can actually record real-time video at 24 frames per second, and got some interesting things here. So this is the video playing on the right. This is just the raw video. I haven't cleaned it up yet. But if we freeze the frame, we can see that really interestingly on the sort of border of the fragmented aurora-like emission on the sort of vertical edge, so not on the bottom like we would expect maybe a pink emission to appear in like an auroral arc. You can see that there's almost like this, I don't even know what it is, maybe like a Doppler shift sort of wavelength, because the fragmented aurora-like emission is moving towards that pink edge. So, and if you actually look at the video, these fragmented aurora-like emissions are moving pretty quick. And then you can see this continuum emission here with the arrow. And then if you look at the video, that's also moving really fast in the video. And so this is kind of where we're at. These are just some discussion points that we can talk about. Maybe there's a possible connection between the continuum emission and the fragmented aurora-like emissions. This is not the only event where we've seen continuum and FAEs, but I just wanted to highlight this one event because of the rich data that we have alongside it. We have the Pfizer measurements, we have the filtered all-sky images that we'll pull down soon. We have the spectrograph readings, we have citizen science observations. And potentially this might be similar to a Steve plus streak scenario, right? Steve is also a continuum emission. We get we have the picket fence, and then we also have the streak. So Steve is kind of coinciding with the fast flow, just like we're seeing in Pfizer with this continuum emission. So maybe there's something there. There's like a parallel process happening. And just in general, there's an open question, I think, of what creates these continuum emissions within the auroral oval. Steve is notably on the equatorward sort of edge of the auroral oval. We see that often with a subauroral ion drift or these Birkeland current boundary flows. And we've seen Steve during quiet times. We've also seen Steve most frequently during active times. But now we're seeing continuum emission really within the auroral oval. And so just kind of closing things off, how do these flows and how does the heating in this continuum event compare to what we're seeing in Steve? I think that could be an interesting comparison. And if there's actually a threshold that needs to be reached to have the emission take place to be visible. So with that, I'll close off and just want to thank the conveners for giving me this opportunity.
Thank you, Vincent. That was very clear. Questions for Vincent? I have. Claire.
Testing, okay. First of all, great talk. Thank you for that. I was interested in particular in the Pfizer measurements, and they kind of went by a little too quickly, I think. Were you able to specifically associate the enhancements and depletions with the continuum emission and or the FAEs?
So I don't think we were able to see the FAEs in Pfizer because those are just too small.
Okay.
And I don't think the beams have that resolution to actually resolve the FAEs, and they're moving pretty quickly as well.
Okay, but with the continuum, are you, I'm not sure if you have a conclusion yet, but are you associating it with a density depletion or an enhancement?
So it looks like there's a density depletion before the continuum, and you can see the heating here, and I think that's the clearest signature in this data.
Okay, thank you very much.
Can I add to that? So just in case this is still ongoing, so Vincent just got the first results. So this is very preliminary. He's absolutely right that the fragmented aurora emission like the fire, it's very, very small scale. So probably we might not be able to resolve that. But for the continuum, he still needs to do that. More questions? Vincent, is this, and for everyone in the audience, to my knowledge, this is the very first time that we see continuum emission measurements in radar data, in coherent scatter radar, right?
Could be. I don't know. I think this field is so young, so it's possible.
We have a ice cat. Sorry,
go ahead.
just jump in. We have a ice cat radar data for the Svalbard continuum, which I'm about to show. So
Yes, Rowan. Yes, second then. Thank you.
Hey, Vince. I had a quick question about the cell phone video that you showed with the pink fringe along the edge of the feature. I don't know a ton about auroral imaging. I'm curious to know a little bit more about that in particular.
Yeah, so this video was captured with, actually it was a DSLR camera, so it's a 4K movie, which means it's a little bit higher resolution maybe than a phone could do, and pretty good quality. It's the raw file, so it needs to be processed a bit more, but I mean, since it's at about, I think it was actually 30 frames per second, this pink fringe that you're seeing definitely was there. It's not an artifact of the imager.
Thank you.
Any more questions? If not, thank you, Vincent. That was great. Our next speaker is actually a ghost. Rowan, are you there?
I'm here.
Do you want to play your slides and then share your screen?
Yeah,
Perfect.
I think I'm sharing my screen.
Perfect.
Can you not see it?
No yet.
Maybe I'll try again.
Okay. I think Vincent was giving you permission to share.
Okay, Fabi, can you see that?
Still not.
Those of us online can see her shared screen.
Okay. Thank you, Christina. I think we're working here. Yeah. To get the
Okay,
perfect.
Fabi,
Go ahead.
so you can see this.
Yes.
Brilliant. Okay. So my name's Rowan Dayton-Oxland. I'm from University of Southampton, and I'm going to be presenting just a kind of a collection of observations that we have of this ghost aurora, which is basically continuum emissions that we see poleward of the oval. So usually in Svalbard, in the day side, when we have polar night, we can observe through noon. So usually we're seeing these like around noonish, and I'm kind of representing a lot of the sort of European sector, I guess. Lots of Svalbard people, Southampton people that have all kind of come together and made a lot of these observations. So I'm just going to throw them all in together and then talk a little bit about some spectral modeling, high resolution spectra, which I think you guys will find interesting. So getting started, like we have an acronym for GHOST, which is a geomagnetically driven high bandwidth optical spectra from the thermosphere, and we've been using the word ghost in the sort of Svalbard community. We like it because it seems appropriate. So this is precipitation-driven kind of continuum aurora. Usually we're seeing it actually in the cusp, so around noon, and it forms both arcs, and we've also seen it forming sort of more like pillar shapes. So these pictures are from some citizen scientists. The left-hand one is a ghost, and it's forming like actually a very tall ray in this image. And yeah, it's a similar sort of pale mauve-ish color, similar to Steve. And as Vincent was just saying, we have it's associated with these fragments of aurora-like emission. So yeah, that's kind of the what is a ghost. So we have identified the continuum in a MIST spectrograph, so sort of proof that it's a continuum, and this is what we use to identify all of our events. I think we have maybe 10, 15 events now. So we take our image from the all sky and we have a spectrograph that looks at the entire slit from north to south, so we can see the whole sky. Here we can extract out the ghost spectrum and compare it to a reference background spectrum, and that's what you can see on this right-hand panel. So what we see here is a continuum spectrum that's very similar to other continuum auroral emissions. It's very similar to the Steve spectrum. So, I mean, what you can identify here is you've got the red and green auroral lines, you've got this blue from sunlight, and then a lot of this other structure in here is different N2 kind of molecular bands. But otherwise, it's fairly flat over the whole optical range. So we have our continuum, and I'm going to show you some more data that's from this same event because we got really lucky. So we got radar data, which is great. So this is with IceCat Svalbard radar. And this sort of like central panel that I've highlighted that's grayed in is we have ghosts kind of appearing for this whole hour of time. It's like really bright, broad arc that was like filling the whole sky. And the kind of main takeaways from this radar data is you can see, similar to what Vince was just showing, actually, we have a lot of heating. So we've got 2,500, 3,000 Kelvin in the ion temperature, and we have up to 4,000 Kelvin in the electron temperature. So this is quite a lot of heating, pretty significant. And we also can see ion upwelling. So this is probably partially to do with the heating and partially to do with the fact that this is actually sort of a daylit ionosphere conditions. We also have Fabry-Perot interferometry data, which kind of just agrees with this stuff, so supports it. So yeah, main thing from this is there is lots of heating and there is upwelling. We also got super lucky with the DMSP overpass. So this is satellite, Defense Meteorological Satellite Program satellite. And you can see here, this is another picture of the ghost. So it's kind of this pale, kind of pinky, orangey stuff is ghost. And you can see DMSP is kind of crossing from north to south over the ghost. And actually when it crosses over between 839 and 848, we can see this like really big difference in the cross-track velocity. So it's going from like -4 kilometers a second to +4 kilometers a second, which is a shear of 8 kilometers a second kind of across this area that I've highlighted. So that's a pretty strong shear. So sort of bringing that into this comparison with Steve, that they both have this kind of associated green aurora-ish emissions like the streaks and the phase. They have the similar appearance and continuum, and actually they're both associated with a very strong ion flow. So that's pretty cool. Nice data to have. Yeah, so now kind of moving on to my instrument. So this is a high resolution spectrograph that we run in Svalbard. And I've highlighted the kind of period where we have ghosts in pink. And if you ignore the orange box for now, even though it's really bright. So on the sort of vertical axis here, we have wavelengths. So this is spectra stacked in time. And this main bright line that you can see horizontally is actually proton aurora. So this is H alpha, and you can see it's brightening, dimming. It's actually very pulsing and patchy, which is kind of not very typical actually in Svalbard at least. And so we actually have identified this as flux transfer events. So this is like patches that are from direct reconnection that are passing over the spectrograph. So this kind of confirms that we are situated in the cusp under kind of active reconnection. And this is what the spectrum looks like. So this is very high resolution instrument, so it's less than 1 angstrom resolution. And yeah, so from this spectrum, this is the black is this bright continuum here that I've highlighted in blue, and the red is background just taken from a bit of time beforehand. So this sort of black spectrum is our ghost. And what you can see is that okay, there's no difference in the proton aurora, so there's no proton component of this. And we do have this kind of continuum A, bright, flat spectrum, but it's clearly a pseudo-continuum. Here you can really kind of clearly see we have this structure. So at this kind of scale, what we'd be looking for is rotational lines from, yeah, kind of vibrational rotational transitions in a molecule. So then looking at, we have 2 more panels. So that was our H-alpha panel. We also can take spectra in the O+ doublet region and for OH airglow. And it's basically the same story repeated. We have this bright continuum, but you can really see that it's pseudo-continuum, and you've got this really structured emission with loads and loads and loads of lines going on. And another interesting thing is it kind of gets dimmer towards the infrared. So this is going into sort of 800 nanometers and onwards. For us, we're measuring that it's dimmer in that region. So then starts what molecule is this race, which involves lots of modeling for me. And I finally got a good fit with really, really hot N2. So this is, so the black line here is the continuum that I was just showing you minus a background. And then the red line here is N2 first positive model at 2000 Kelvin. So that's 2000 Kelvin for both vibrational and rotational temperatures. And this is the spectrum that we get out. And you see it's a pretty good fit for the overall shape, and it's got quite a few lines that are fitting nicely as well. So this is pretty interesting, and yeah, we wouldn't necessarily expect it to be a perfect fit yet, because it's early days of the modeling. It's quite a coarse guess. But then I extended this to look at a few more events and say, okay, maybe I'm just looking at N2. Let's look at some more continuum events. And this is the fit that I have on 2 other events. So you can see here, again, it's the black is the measured continuum spectrum, and the red and the blue are the model. I can see that quite a few of the lines are kind of fitting, but the overall shape, these lines are fitting pretty well, but the overall shape is clearly fitting pretty well. So, and this is at 3000 Kelvin. So basically what we're thinking and working on is, if this is really, really hot N2, several thousands of Kelvin, because as the temperature increases, all these vibrational bands kind of shallow and broaden, so they become more continuum-like. And actually, we think of these sort of discrete areas where you've got N2 emissions, but we also have lots of other parts of the N2 molecule that, if it gets hot enough, these could also be emitting. So we're kind of extending our modeling now into, we've got Vega Kaplan, we're working on infrared afterglow, first positive, second positive, so lots of different states. And we're kind of also trying to include the possibility that this might be non-thermalized, so the vibrational and rotational temperatures might be different from each other. So there's a lot of complexity that means that we wouldn't necessarily expect whatever model we have right now to be a perfect fit. And we might expect the temperatures to actually be much, much higher than, for example, IceCap would suggest. Because fine scale structure, quite often high temperatures can be lost when you just measure on a kind of coarse grid. But fine scale structures where you've got these very, very strong electric fields in a very small region, you can get much, much hotter temperatures. So yeah, we're working on that at the moment and submitting a paper next month. So keep your eyes out. And yeah, that's everything for me really. This is the ghost paper here, the QR code, and kind of put some points for maybe discussion. And I included some citizen science pictures. So if you want to know how to interact with citizen scientists, there's a handy handbook that me and many other people in this session have worked on. And that's me.
Thank you, Rowan. That's fantastic work that you have been doing. Questions for Rowan? Yeah.
Yeah, hi, Rowan. This is Phil Erickson at Haystack. That was a very nice talk. Could you go back to the DMSP data for a moment there?
Yep.
Yeah, what I'm a little surprised about is, given what I know about the DMSP meter, it's interesting. It appears to be pegging at 5 kilometers per second. That's a little higher than I would have normally expected. From other data I've seen, it kind of pegs at 4. So I agree with you that the thing is changing sign, certainly right there in the middle, but I don't know if you've had anybody else pass their eye over the DMSP velocity measurements. It might be a good idea to do that.
So this isn't actually this is from someone else's piece of work, and this is published. So I don't know, I'm not a DMSP person really. This is somebody else's result.
Gotcha. Yeah, it's just that Right. Okay. Yeah, maybe I can follow with a little bit later. This is the meter was never designed to deal with this level of velocity, and it just saturates at some point. You can actually see that in your red curve right there. All of those points that just kind of don't go any higher than 5, you can see that. So just as long as somebody's treating that correctly, but the shear is certainly very, and for your conclusion, the shear is the important thing, and I think that's definitely robust. It's very, very fascinating, actually.
Thank you.
As a note, so Toshi just look at this data, but we haven't talked to Phil Anderson, for example, so that's hard to do. Any more questions for Rowan? I have a question for the audience. Are those plasma velocities common in the CASP? I'm not a CASP person. Mm-hmm. Yeah, we need a Svalbard person, yeah. Yeah, I think all of us are too lower latitude. So I think that's something that we might need to answer in the future. Is this common? How common it is? Every time that we see something like this, are we observing a continuum emission? Because that would be an easy reverse study to do.
So I think in Svalbard, they're getting a new PhD student to work on continuum, and I think that's one of their main things they're going to be doing is kind of what is the difference between the sort of typical conditions and the continuum conditions. So that should be interesting.
Oh, that's fantastic.
Bea, can I ask a question?
Yes, go ahead.
Yeah, thank you. This is very beautiful. Thank you. I had a question about actually the comment that's on your second bullet here. You say that this event is precipitation driven, and I was wondering why you think that would be true. What indication do you have that it's precipitation driven?
That's a very good question. I know that, so I'm not the first author of this main paper, and I think there might be some satellite data involved in it, but at least from my understanding, the kind of dynamics of the ghosts when you see them and the fact that they form these like long field line structures, they kind of form these like moving pillars, it kind of looks just like kind of normal precipitation-based aurora.
Yeah, I would agree with that. I was just really curious to know if there was anything to pin that on. Is there somebody who would be more familiar that I could follow up with?
Nora.
Okay.
Yeah.
Yeah, sure.
But
thank you. I'll ask her.
This paper I've taken like little bits out of this paper to sort of highlight for this session. So that would be the place to go.
Great. Thank you.
Oh, thank you.
Hi, very nice talk. I just had a really quick question. I may have missed this, but what latitudes do these usually occur at?
So all of our observations are from Svalbard. So we're at 78 degrees. But yeah, I guess it depends on how you're defining like ghost. I mean, because we're poleward of the oval, like it's quite hard to look poleward of the oval and also to look in the day side and in the cusp. It's really Svalbard's the only place where you can see it. So we don't have any people looking in other kind of longitudes. So we're kind of limited to Svalbard. So then we're at 78 degrees north for every single observation. But yeah, it'd be very interesting to see whether any of the other, it's hard, there's not really anywhere else to observe stuff that's so far north. I can't think of any other examples of poleward, kind of separated poleward stuff, but at least in the cusp, then it's only in Svalbard that you can see it.
Hi, Rowan. This is Claire Gascoigne from the University of California, Berkeley. This is really, really interesting work. I had a question about the chemistry that you're looking into. So for a lot of the other continuum phenomena, one of the leading candidates is essentially NO combining with oxygen to create NO2 and continuum emission. I'm wondering if you've looked into that at all, or sort of what your path is for the chemistry here.
Yeah, so we started off trying to look for the NO and it failed. I mean, we're trying to look for, in our spectra that we have, in this high resolution spectra at least, we only kind of have this sort of very red end. So we were kind of trying to look for the N2 that was energized enough, so like your Vigor Kaplan bands that would then be able to produce the NO, so it could go through that mechanism. So we were trying to look for those signatures, didn't find them, and I know that we have compared the NO2 spectrum to the whole MIST spectrum, so the sort of wider, coarser spectra that I showed at the beginning, and we didn't really get anywhere with that either. And I know with like June's recent work, looking at the quantum stuff, maybe the NO mechanism's a bit like, maybe it's not great for Steve either. So we were kind of thinking, okay, it's really hard to make enough NO for it to be so bright. And these ghosts really do fill the sky very brightly. And we know we've got lots of like sort of N2 being upwelled. We know that it's there, and it's sunlit, it has this shear, it has this precipitation, it seems to fit. So we kind of then like, I've kind of gone into that side of things, because we don't have a kind of clear signature for NO2 that we can find, but we have tried, and it's the first thing that we considered, and then we kind of got distracted by this, like, oh, it actually fits really well. Like, when I got this spectrum and I got this fit, I was like, okay, this is like a new avenue for hopefully me and other people to be thinking about. We'll see where this modeling takes us.
Okay, thank you so much.
Thank you, Rowan. I think, okay, you want to hold your question, June?
Yeah.
Okay. Thank you so much, Rowan. Rowan is a student at Southampton who's joining us remotely. Thank you for making the time to join us today. That was great.
Thank you. Thank you for the discussion.
So now we have a University of Calgary team, Emma Spanswick and Josh. Josh, you have to say your last name before I butcher.
I can try. All right, thanks, Bea. In an effort to not steal the thunder of my student, he's up here, and we're going to tag team this talk because he did a large fraction of the work, and he's going to be continuing on. So what we're going to be talking about now is basically the University of Calgary, our experience with how the continuum mission came about for us. And it follows really on from the Steve experience, and I would say, and that's the development of capacity to image. And you can look at the historical trends that we've had, with narrowband auroral imaging, then the white light from Themis, and then we followed that on with T-Rex. And the idea of the T-Rex RGB was simply to get the information that we have from Themis, but to provide a publicly, engaging image. And what eventually ended up happening was, as we were commissioning these instruments and looking through the data, we ended up with one of those moments of, what is that? Where we're looking at the data in the morning, and we notice things in the data that don't quite look like what we would typically associate with the aurora. And so this is one of these structures that we were able to observe in the T-Rex RGB. At the top, you've got a keogram from RGB that's showing at the time of two images that are below. And you can see this sort of white tinged blob that's sitting on top of this green dynamic aurora. And on top of that, there's a field of view. That line that's cutting across it is a field of view of the meridian imaging spectrograph. And so we have full spectral measurements along this line. And as that white tinged blob moves across the field of view of the spectrograph, you've got those two spectra that are below. And so you can see the dot that's in red before that blob appears in the spectrograph field of view. We've got this level of luminosity, which looks like either very weak aurora that the imager's not really picking up, or background air glow. And then as this white tinged blob comes across, you see this elevation of the entire spectra on top of that. And that is what we mean when we found the continuum emission, or we were able to image what I would say is the structure of that continuum emission, which is very, very different than other continuum emission that we had seen. Now, of course, the idea of continuum emission, it's not new at all. You can go back in the literature, even well before Steve, and you can find measurements that were spectroscopic, kind of single pixel looking up. And there's evidence in the literature of these unexplained continuum emissions that were during the dynamic aurora. But of course, The technology wasn't there at the time to be able to image the structure of that. You just had the spectral measurements, so you knew that there was dynamic aurora, and you knew that the continuum was there, but you didn't have the information to be able to follow it or look at the structure or the dynamics of how it's evolving. And that's what we've got now. And so I will turn it over now to Josh to talk about how we quantified some of the structure. Go for it, Josh.
Hi, yeah, I'm Josh Houghton. I'm an undergrad student working at the University of Calgary. And like Emma said, I was involved in this first paper, doing some of the work there, and I am now, through my undergraduate thesis, I'm working on kind of the continuation of this last paper that we just put out. And so basically, what I've been kind of looking at is, we have these events now. We have originally 32 events, and now I've extended that to 52 of these structures that we've observed in the T-Rex RGB data and confirmed with the T-Rex spectrographs. And I'm basically trying to look at, what's going on overall, both globally and more locally in the ionosphere related to these emissions. So, we see this dynamic aurora, and you'll see one spot where this sort of structure kind of emerges within or alongside the aurora. But right next to it, there's no sign of a continuum emission. So I'm kind of trying to look at what's special about these regions where they do appear versus where they don't. So first of all, kind of looking at the global perspective. So overall activity levels that we see alongside these 52 structures. These are superimposed epoch analyses of two indices. So we have the KP and the DST indices, sorry. And so immediately you see there's this clear kind of association with very active conditions. I also noticed in Vincent's talk that his DST plot kind of fits into the statistics of of what we have here, which is interesting and good, hopefully. And what's really interesting about these plots is in both cases we see, not only are they occurring during very active conditions, but we see that in both cases, the observation of these emissions is occurring right at the peak in KP and right around a minimum in DST, which says something about that these emissions seem to be observed at the most active times. And so that's kind of the global perspective. And I'm going to put up this slide. I'm not going to go through everything in detail because I kind of want to plug my poster, which is tomorrow, and all of this can be found there. But this is the kind of more local perspective that I'm taking. So kind of trying to look at what's going on locally in the ionosphere. And I'm doing that, so the top right plot is just the raw T-Rex RGB data. And I'm, again, trying to look at, what's different between these spots where we see this emission and where we don't. And so that's a comparison just using the raw T-Rex RGB data. And then I've also began to try and utilize a auroral transport model that Jun Liang right here has been working on for quite some time. So trying to kind of quantify what sort of energy flux, like what sort of precipitation are we seeing actually being associated with these emissions? Because, the fact that they are appearing right embedded in the aurora or alongside the aurora is very interesting because that's kind of a major distinguishing factor of these continuum structures when we look at Steve, which is, completely detached from the aurora. So that bottom left plot is kind of the first results I've gotten from the analysis with the auroral transport model. And then that bottom right plot is my first attempt at kind of trying to map the precipitation or map the energy flux that we're getting out of this auroral transport model associated with one of these structures that we can see optically in T-Rex RGB. So I'm going to leave it there and just kind of open it up to discussion or any questions. So thank you.
Thank you so much. That was wonderful questions. Carlos.
You showed DST and KP indices, and they show exactly that, it's 0 time for the maximum. Did you have a chance to look at other indices like AE or AL?
Yes. Yeah, I chose these two. These are the first two I looked at. I've been looking at a plethora. So I looked at it's the SML, like the SuperMeg AL counterpart. Again, I'd love to show those plots if you want to chat after or come to my poster. Okay. There is some interesting behavior in that plot that we're not quite sure how to interpret yet. Okay. We have looked into that. I've looked into, and actually similar to what, again, Vincent noticed with his event, looking at like solar wind conditions and IMF conditions. There wasn't really anything interesting there. But yeah, definitely there's something with AL that's a little bit interesting. So
thank you.
Yeah.
Yeah, so my name is Jeff Reeves. In the previous talk, we were seeing these kinds of forms at very high latitude, so well above the auroral zone. You're saying that you're seeing them next to the discrete aurora. Are they always on the north side of the discrete aurora, or do you just see them everywhere?
Great question, Jeff. So these ones, when we're seeing it, and we can go back to Josh's first slide there.
That's a little hard to see.
It's a little hard to see, but you can kind of see he's circled some of the locations of the continuum emission. Each one of these was confirmed with the spectrograph, by the way, so we've got confirmation of the continuum, but they're actually embedded in various regions in the aurora. Some are to the south, some are to the north. In terms of commenting on the polar cap versus auroral nature, I think what's going on with the continuum is there's going to be different mechanisms that can drive it. Because clearly with Steve, it's this like high-speed flow, right? But when we start looking at these types of structures, again, as Josh said, why is that particular blob glowing and not the region right next to it, right? So understanding how that works in this scenario is a little different. The polar cap stuff looked again like more like flow style driven with precipitation on top. And what Josh is showing here, when we looked at the energy flux, I think is also giving us some information, the fact that they're in storms and we've got kind of a puffed up thermosphere, and then all of a sudden there's a high energy flux right in that region. And so what's causing that energy flux? I think we're going to find that there's lots of different ways that you can trigger the continuum to glow, and maybe it's different chemistry in different cases.
And have you done the subtraction like she did of the background versus the continuum?
100%. Yeah.
Are the spectra similar?
Yeah, and in these cases, so what we see in these cases is that there is a distinct auroral component as well. So we get a continuum elevation and we get enhancement of the lines. So it's not as much like Steve, where it's like a step in background and there's no additional auroral component. In these ones, we have distinct auroral enhancement during the continuum emission.
Thank you.
Can you said one part of what I was going to say, but just for Jeff, the spectral resolution of the Svalbard spectrograph is 10 times better than ours,
yeah, it's better.
right? And so there's a lot more structure, like small scale structure in their spectra. And the other thing I was going to say, but I mean Emma sort of said it, but I mean I think Steve is flow driven. Right, and this stuff I think is precipitation driven, and then the thing in the cusp, is sitting there with what is a velocity that's kind of slow for a Steve, but super fast still, right? And so it might just be some kind of the ghosts might be some kind of combination of both.
Yeah, to me it's almost like there's a tipping point.
Yeah.
Right, and there's multiple ways to accomplish that. And if you've got enough flow, you've got Steve. Right? You don't need the auroral element of it.
Right.
And in the polar cap, it looks like you've got both. And here the question is, what's going on with the flow structure? I don't know. But they're clearly not, like there's no east-west preferred alignment. There's no anything. The structures are all over the place.
And the velocities, just by looking at the aurora, the velocities are nowhere near Steve velocities.
But
Right?
these ones are also occurring during storms. And so I think that's another indicator. We've got another source of that energy just by the fact that you're depositing a bunch of energy into the ionosphere.
A source of the energy and changing of the
thermosphere.
composition in the thermosphere.
Right? So I feel like there's going to be a tipping point where we engage a certain chemistry.
Yeah.
Any more questions? Anyone online? So I do think that is a good discussion because it's not only, when we talk about the generation mechanism, we are not only talking about the chemistry that we don't understand, it's also the dynamic and how the dynamic changes because of the chemical changes. So it's very intertwined.
And now it's what can create a structure that's of that kind of size with no preferential alignment in which you're dumping a bunch of energy flux in. So there's got to be a magnetospheric source for that, and now so there's an engagement of the magnetosphere into an already primed ionosphere. And then figuring out, unfolding that is going to be fun.
Exactly, and as last comment before I change the slides, the results with DST is very similar to what we see for Steve. So that's also very interesting, thinking about the magnetosphere. Thank you both. Okay, our next speaker is Jun Liang.
So I'm just going to talk about some kind of the modeling efforts of this sort of the aurora continuum structures, and I will just be quickly to summarize the progress we have made and the challenges I encountered and what I need help from the community. And so I think that Emma already gave a kind of a very good introduction to this sort of aurora continuum structures, and for more details, you can just look into our paper. So this is what Josh talked about, the superposed epoch analysis. I just want to emphasize two things here. So, this is the red. Okay, so the first thing, as I mentioned, it always occurred the perfect line with the maximum KP epoch. And if you look into that, there's actually the KP threshold of the minimum threshold of the KP4 there. So this is a kind of aurora continuum. Obviously, this is not a kind of the quiet time interval things. It's during the extended active intervals. And the other things, if you look into the DST, the superposed analysis for the DST, it's always occurred, almost exclusive occurred during the storm time, and it's occurred during the main phase of the storm time, and roughly occurred at the minimum, the DST epoch. So there's a lot of kind of the storm pipe precondition of the neutral atmosphere that occurred before this sort of the aurora continuum occurrence. So, okay, so yeah, this talk I will just be doing some kind of event-oriented kind of the simulation and the comparison. Now the event I'm looking at is during the Canada Thanksgiving Day, and if you look into the curve structure here, that's a kind of aurora continuum that we are looking into. I sampled the structure of that, and on the right side the panel. So basically, we have got a bunch of the aurora lines there, so it's clear aurora. And we also see a kind of the enhancement of over the broad of the wavelength range, which is the nature of the continuum emission. And in this event, they have a very high quality, the imager and the spectrograph observations, so we can get for example, the green line intensities, the blue line intensities, which constitute the base for the comparison between the model and the observations. And we don't have kind of the in situ flows, such as DMSB in situ flow measurements here, but as many people have already mentioned, like the previous study by, for example, Bear, and the optical flows is kind of a way to estimate the convection flows. And this is the way of doing that is through so-called evogram. So yeah, I plot the movie on the right side, and if you look into the slant trees on the evogram, they indicate a kind of the eastward propagation here. here. And from that trace, we can evaluate the velocity of the optical structure and in turn the plasma flows. So yeah, so well, I have to say that the mechanism for the continuum is not clear yet, but the thing that we propose nowadays propose the most, and the kind of the model, I call it modelable, the mechanism in this so-called NO2 continuum. And so basically this kind of reaction between the nitric oxide and the oxygen. So obviously the nitric oxide is the key thing there. There's a number of the conventional ways to produce the nitric oxide, but they're not enough. The thing we specifically look at is the reaction between the nitrogen molecule and the oxygen, but that requires a high energy threshold there. And that basically requires we need a kind of electron impact to cause the high energy, the high vibration level excitation of the nitrogens, or we need some sort of the vibrational translational, the exchange of the vibrational excitation led by fast ions. And I just mentioned that this kind of the cross-section and the rate coefficients, that was already obtained through my previous studies. So in the model, they're already embedded in the T-Rex ATM model. So we're able to model this process. So yeah, this is actually the model setup here. So I assume this is the 5 kilometer flows. That is the invert from the evogram, the optical flows. And I assume the kind of the maximum precipitation with the 50 erg per square centimeter per second total flux, and the 4 keV, the characteristic energy here. So this is to give an example here of what I achieved, the temperature profile I achieved, the electron ion and the neutral temperatures. I just quickly mentioned that you see the spikes in the electron temperature, that's the anomalous electron heating effect. And this one thing I have to mention that in my model, we don't have a kind of a neutral component in my model. So I have to use a kind of this empirical model like MSSE. But just following the suggestion of Dr. Chen Shen, I just ad hoc add a kind of the 30% increase in the temperature to account for the very strong heating during this sort of the event intervals. So yeah, I'm just giving a kind of show you. I'm not going into details, but time is limited. Just keep, how to play this. Okay, so this is the nitrogen vibrational, the evolution. So the horizontal axis here is the vibrational states, and the vertical axis is here is the altitude. As you can see, there's a kind of very strong the excitation of the N2 vibrationals into the high vibrational states, and this occurred at a kind of altitude about 110 kilometers, which is exactly where you see the anomalous electron heating here. So, and the nitric oxide density can reach several of the 10 to the power of 9 per cubic centimeter. So, okay. So, how to go? Okay. It seems stuck here. Hello? Okay, so this is actually the model. The model, the optical intensity compared with what we observe, the observations. So the first one is the green line. So yeah, I already the thermal contributions of the thermal electrons here, following the suggestion of Brian. So, and the second is the blue line intensity. And the bottom panel is about the key interest here is the model, the continuum intensity versus the actually observed continuum intensity here. So obviously, so it's kind of, we can get some sort of the order of magnitude agreement between the model, the continuum, and the observations. But yeah, I have to say there's a kind of the uncertainty and with the model. The first, as I mentioned, I don't have a kind of neutral the component in my model. I have to assume kind of the things from the neutral profiles. And the second thing here is I want to mention is if you look into the rise time of the continuum intensity, well, this is a little bit slower than I expected. So it takes about a couple of minutes to rise. This is a bit slow. Why this is the key issue here? So because think about it, my model is one-dimensional, but the precipitation structure is fast-moving with sort of the 5 kilometers per second. Neutrals can't follow that speed. Neutrals is relatively immobile. So what caused this is kind of here. So, okay. So can you see the movie? There's nothing there. Really? Okay. So every time I want to play a movie, I have technical. Okay, just to quickly explain what happens. So you have kind of fast-moving precipitation structure here, and neutrals inside the precipitation get heated and produce kind of nitric oxide emissions, but the intensity they can reach relies on the time it stays in the precipitation structure because it's precipitation and flow driven. So it stays in the precipitation structure. That caps the maximum intensity achieved during this sort of the process. And there are two deductions that infer from this process here. The first, the strongest neutral intensification tends to occur at the trailing edge. For example, you have an eastward moving structure. The strongest neutral intensification actually occur on the western edge of the aurora structures. And so this is actually what we saw from some of the observations. I'll give a quick example here. That's from the MS paper. So we have kind of the green structure on the east side, but the continuum actually the white hinted the stuffs actually located on the western edge of the aurora structure. So it makes some sense. But the key issue here, consider kind of the scale size of the structure, which is kind of 100 kilometers, and if we assume 200 kilometers, we assume the 5 kilometers per second. The time the neutral stays in the structure is only about a few tenths of the seconds. But as I said, the rest of time for this sort of continuum from my simulation takes about a couple of minutes to rise. So yeah, this is the key difficulty I ran into here. So, okay, so just this is my final stats. I just mentioned that the first law from the results I already achieved, the NO2 continuum appears to be the one plausible candidate mechanism of the aurora continuum structures because, well, I can make the kind of order of magnitude the kind of agreement here. But to make it a kind of quantitatively closer to observations, a pre-enhancement of the neutral and the self-consistent neutral variations needs to be considered. And I just quickly mentioned that the key components I need to kind of the so-called the precondition is the first of all is NO2 continuum. I need the NO2 density, the nitrogen densities and the oxygen densities, and also the neutral temperatures, and also need kind of some sort of the initial or high initial level of the nitrogen atoms. That this is the key thing that determines the rise up time of this sort of aurora continuum structure. So yeah, basically, so I think the coupling to the global IT models to include the precondition and the self-consistent variation with the neutral atmosphere is required for this sort of the model efforts to proceed. Yeah, that's all. Thank you.
Thank you, June. Questions for June?
Yeah, very interesting. This maybe isn't as directly related to your talk, but since you mentioned it about the timing with respect to KP and DST. Mm-hmm. So Emma had mentioned maybe having some sort of threshold effect. This superposed epoch is not suggesting a threshold. What it's suggesting to me is that when KP starts to decrease again, you've turned off the cross-tail electric field. So you've got increasing convection, and then you stop convection. That's consistent with DST as well.
Oh, okay.
So your chemical reaction rates are much faster than what would show up in any kind of superposed epoch plot.
Oh, yeah, sure.
But I'm wondering, is there anything in those equations that might be sensitive to that change of convection? Because that might be a key. That's what the superposed epoch is suggesting.
Not in the chemical, but I think the fast flows is required for the heating because this relies on the strong heatings. But so the flows, if the flows occur before this, that will be kind of also called the precondition. Also, they will be include the precondition, give some sort of kind of the level, the starting level of for example, the nitric oxide, the nitrogen, some sort of that. Yeah, that's possible, but that's not included in the current model yet. I think that needs some sort of the global models to actually include that effect.
But if it was something like heat flux related to the convection, you'd expect to see a thresholding kind of effect, not things to happen at the peak.
The peak is when it changes.
But
Anyways,
this,
something to
this is
think
the
about.
KP. This is kind of the long-term interval averages of that. So.
Thank you for the talk. Can you please comment on your ion temperature?
Yes, sure. This is I noticed that in the presented ion temperature is a kind of few thousand, and what I modeled here is kind of the 10,000, more than 20,000 or something. I'm not sure it's a kind of the realistic or not, but I think I've taken into all the kind of there's a sort of, for example, the collision loss with the vibrational collision loss with the neutrals. I think I include all the source there. The only thing I miss here is the Maximilian effect. The Maximilian effect, this can be done by the model. And I agree with that will be very important in that high temperatures. So yeah, I will try to kind of increase the accuracy of the ion temperature. I'm not saying this is accurate. So this is probably problematic, but this is so far I can achieve this.
On a side note, I know Toshi Nishimura and Dave Knudsen have been working on getting ion temperatures from SWARM. So that's a result that we are going to have in the near future. Yes. Yeah. Good question. Thank you so much, June. That was wonderful. Our next speaker is Brian Harding.
Okay, well, thanks for the opportunity to talk about some of the ongoing modeling that Claire and I are doing to try to put constraints on the conditions under which we can get continuum emission, theoretically. Our focus is on Steve, not on the continuum aurora. Those may or may not be different, but this talk is about Steve. And so, as we all know, the real challenge, theoretically, here is to predict the spectrum. And the spectrum mostly comes from the measurements from Calgary. The bottom here, I'm showing the Gillies et al. Spectrum. One point I want to make is that any successful theory needs to match the observations, but it also needs to match what's not observed. And so 95% of the light here, the visible light spectrum, is from continuum. There's a small, about 5% component from red line, according to the observations. There may or may not be green line. It's kind of within the error bars, but it's clear that there's not a lot of red line and there's not a lot of green line. Okay, so I'll come back to that later. Okay, I want to take a minute, and I hope it's okay, to talk through the theoretical thinking here. And the reason I want to step through this is because I want to sort of give everyone a chance to poke holes in certain places, because one of my conclusions is I think we need more theoretical ideas. Okay, so as Joan mentioned, the main thinking right now of where this continuum emission comes from is from the NO2 emission. It's well known that if you have enough nitric oxide, it reacts with background atomic oxygen to create NO2 and a continuum of light. This is well known. It's actually, there was papers in the 80s and 90s talking about how you get this continuum emission on the RAM surface of the space shuttle. And they did a lot of work on this, actually, and we're pretty sure, and I would say pretty convincing, that this is from nitric oxide creating NO2, creating emission. But they had no idea where all the nitric oxide was coming from. Okay, I think there might be a very interesting analogy between a space shuttle moving at 7 kilometers per second through the neutral atmosphere and these really fast flows moving at 4+ kilometers per second through the neutral atmosphere. Okay, and we also know as Emma mentioned, since the 70s or 80s, that there's a continuum emission component in the aurora. We didn't know it was as strong as the cases that Emma and the Calgary crew were showing, but we knew it was there a little bit, and there was pretty convincing evidence back then that that was from nitric oxide. So this seems to be where people's heads are now. But how do you get that much nitric oxide? Well, to turn N2 into nitric oxide, the difference in the bonding energies is 3 eV. So you need 3 eV of energy to sort of kick off this reaction. Well, where does that energy come from? The first place you might think about is the first electronic excited state of N2, that's N2A. We know this happens in the daytime, we know this happens in the aurora, so this might be the first place you look. I won't talk about it too much, but our tests show that that produces way too much green line. So I'm going to put a big green X through that. The other case, you only need 3 eV, okay? You don't need the 6 eV that it takes to excite N2 electronically. So you can get 3 eV through vibrational excitation of N2. What we thought back in 2020, well, we showed in our paper in 2020 that if you get enough N2, and this now we know is a very large number, but if you have 5% of N2 in those high vibrational states, you can get a Steve-like emission that kicks off the rest of this chemistry. And what we thought back then was, well, what's the special thing about Steve? Well, Steve occurs where these fast flows are. And so we thought just bombardment by these fast ions might be able to excite enough vibrational nitrogen. But then Jun Liang and Eric Donovan came along and showed that if you do the quantum calculation of the cross-section correctly, you find that it's a few orders of magnitude too slow. Okay, so that pathway doesn't work. Where does that leave us? Well, the only other thing I can think of, and this is what Jun Liang's presentation was just about, was electrons. And this is a viable pathway. I mean, this happens during the daytime. It happens in the aurora. In fact, this pathway of vibrational excitation is the main way that the ionospheric electron population cools itself off. So it stands to reason that if you have a hot electron temperature, maybe this is accelerated. I'll do just a quick, almost back of the envelope calculation here to talk about that. Here's the different cross sections for electron impact. The gray is vibrational distribution of nitrogen. The red is exciting the O singlet D state that produces the red line emission. The green is the same thing for the green line emission. So what I did here is I just took Maxwellian distributions of the electrons, convolved them with those cross sections of N2V. I just added them all up for this calculation of all the N2V, equated that with the loss of N2V through collisions with O, and asked what's the equilibrium population of those high states. And you could see there's this, Emma called it a tipping point. There's this tipping point in the theory above about 4,000 Kelvin where you start to get a significant fraction of N2 vibrational distribution. Now, where does that excitation happen? I don't know, but just for the sake of this back of the envelope, let's say it comes from anomalous electron heating. Cases where you get really fast, really strong electric fields cause ions and electrons to move in different directions faster than the ion acoustic speed that produces all these instabilities that heats up the electrons. So that's complicated, but there's this very simple relationship from this paper by St. Maurice and Goodwin. So all I did was use that relationship to change the x-axis to E cross B drift speed. You find then that the tipping point happens around, I don't know, 3,000 or 4,000 kilometers where you get significant vibrational excitation. Well, Bill Archer also found this tipping point in the data that said that Steve only happens when you get 4 kilometer per second flows. So this is all to say that maybe this seems viable. So we wanted to test it with a model, test it quantitatively. So this model we've been working on is essentially a way of combining Claire's work recently with my work from 2020. It takes an electron energy distribution. This could be anything you want, from GLOW or from a Maxwellian assumption or what have you. And it calculates the time history of the species densities and the optical emissions that you get out. I want to just make the point, this is a very simple model. It's not meant to be fancy. In many ways, it's a simpler version of the work that Jun's doing, but it's meant to just kind of put constraints on what are the conditions necessary to produce the continuum. Okay, and we still have some work to do in the cross sections and such, but this is kind of a preliminary report. To show us an action, I'll just show a simple case where I have a 10,000 Kelvin electron population, a pretty dense electron density, and at 110 kilometers, and it shows that like the N2 vibrational distribution, that's the different bars in blue here, sort of slowly ramps up. This is definitely an extreme case, but the point of this model is to investigate these extreme cases. Okay, so what I'm going to do, and this is the one analysis I'll show, is I'm going to just assume that the electron distribution is monoenergetic. It's like a delta function in energy, and I'm not doing that because that's realistic. It's not, but I'm doing it because it's a way that we can probe and test the parameter space to test, under what energies is it even possible to get a Steve-like emission. And there's good news and bad news, okay? The good news is that the model produces continuum. Under these cases, 140 kilometer altitude, 10 to the 6th density, and a 5-minute duration. The bad news is it also produces a bunch of other emissions. So here's the red line, and this is a log scale, by the way. Obviously, if you get above 4 eV, you start producing a bunch of green, so that's ruled out. Once you get right to 2 eV, at least in our model, you're getting a ton of red line, which is just not observed. So there's really only a tiny range here between about 1.8 and 2 eV, where you get a spectrum that even looks close to Steve. And it's too dim, and it requires too much density. So where does that leave us? Well, like I said, this modeling is preliminary, so I'm not prepared to put a big red X through that top left one. But so far, we're finding it difficult to make this pathway work, except for these very narrow cases. This pathway might work in the auroral case, like Jun was showing. But as you mentioned, the rise time for that is a bit long as well. So I'm just kind of left with the nagging feeling that we're missing something. Maybe there's something that accelerates one of these lines. I think the vibrational distribution of NO might be really important. Or maybe there's total other sources of continuum. I'll just leave it with with my opinion on what's needed to make progress theoretically. And this is not meant to criticize the observational community. We wouldn't be here without them, but it's what I think we need in order to make some progress. One is the altitudes. I think there's only a couple of papers that describe the altitudes of the continuum. There's papers on the altitudes of the red line, but the altitudes of the continuum are super important, especially if anomalous electron heating is involved. That's only a very narrow range of altitudes. And then the timescales. Toshi started this a little bit in his paper, but I think a careful analysis of the optical timescales might actually be able to rule out NO completely. So that's another possibility. And then obviously in situ measurements. So, okay, I'll leave it at that. Thanks for your time.
Thank you, Brian. Questions for Brian? Carlos has a question.
Thank you, Ryan. Very nice presentation and walking us through the different options to get these emissions. So you mentioned 2 times heights where you were doing the calculations. First, 110 kilometers, and then you moved to 140 kilometers. When Steve is observed, many times we've seen altitudes as high as 200 kilometers. So this is something similar to your initial paper, that your explanation was good to lower altitudes. So in the current calculations, how better or worse would be if everything were done at 200 kilometers?
I think the higher you get, the harder it is, and it gets harder very quickly. If you tell me that there's a continuum emission up at 200 kilometers, and that happens all the time, not red line emission, not single bandpass emission, but continuum emission up at 200, then I think we got to kind of, I'll go out on a limb and say we should scrap most of this and try to come up with some new idea.
Okay, thank you.
Okay, yeah, I'm not an imager person, right? As you might know, but you were saying it gets hard in a hurry as you get up to 200 kilometers. Where is the boundary where it gets really hard in a hurry? I'm just trying to figure out how well you'd need to constrain the altitudes.
Yeah, maybe a number to start with is the neutral scale height, which is like 50 kilometers up high down to, I don't know, 20, I'm just guessing, but maybe around 130, it's like 20 kilometers, so.
Okay, so at that point, it just gets to be really, really hard to figure this, if it gets higher than that.
Yeah.
Okay.
Jun, go ahead.
Yeah, so nice talk here. So just quickly comments here. So the question I just want to ask to Ryan's the previous talk, the person in her event described it comes up very strong red line, future super strong red line if you look into the spectral graph. So that's one of your difficulty here. So and the other things, yeah. So as we discussed before, the key thing is here the electron density is here. So still in my mind, so you assume kind of 10 to the power of 5 or 6. Which in my model I produced less than 1,000 in my model, but we don't know yet. So the thing is, we don't know. We don't know is there any kind of the mechanism. For example, the local acceleration will cause the electron density increase, locally increase there. So yeah, I think it's not kind of excluded mechanism, but we have to sort out many kind of the unknown the mechanism there.
Yeah, I totally agree. I mean, the characteristic of Steve is it should be in this channel of depleted density.
Yes.
Right. So that makes it even harder. Any mechanism that starts with E is automatically disadvantaged. But maybe it's sort of just outside the depletion, or I don't know.
Yeah.
Rowan, go ahead.
Yeah, this is super nice modeling. I guess my question was, obviously we've been looking at N2 as an alternative to NO, since it seems like there are like quite a lot of barriers to the NO mechanism being bright enough. Do you have any capacity in this model to like look at how bright would that, you have all this vibrationally excited N2 to produce the NO, like can you model, what would the emission from those species be?
From the vibrationally enhanced nitrogen itself?
Yeah.
Yeah, I'm actually, maybe someone in this room knows better than me. I'm not aware of a very strong, you'd think there'd be infrared emission at least from that. But my understanding is that the main loss mechanism is VV collisions and collisions, other quenching collisions, and not emission directly. But maybe one of the excited states, I don't know.
Just quickly comment. In the aurora continuum, we do notice that the existence of the vibrational lines, the nitrogen vibration lines at high vibrational states. And I actually did that sort of the calculation, and it agrees with the observations. So it could contribute to some of our observed aurora continuum for sure, but it can't explain the overall the continuum.
From N2 first positive, or what's the?
It's mainly in the line of the second positive group, positive, so the N2 second positive group.
But certainly that alone can't explain the whole continuum.
No way.
Right.
Yeah.
Thank you, Brian. That was great. Is there another question? No.
Can I say one more thing?
Yeah, go ahead. I'll change slides. Well, you can.
On sort of N2, we've been modeling, we have first positive, second positive, but also, if you consider high vibrational excitement and you consider sort of N2A is then able to emit kind of throughout the entire optical spectrum. There are these N2A bands, and there's also this IR afterglow, which also emits in the optical range. So I think, when you look at very, very excited, very hot N2, there are, more bands are available, I guess, than the ones that we traditionally model.
Well, just briefly, I guess I thought the VK bands were mostly ultraviolet, but it sounds like we should talk, and it sounds like, we should create a model that produces all the emissions and not just a few. So, thank you.
I agree. I think my intuition is that it's just my intuition, but, that we have maybe multiple species all emitting, all on top of each other. But yeah, we should talk.
Could be. Yeah, I didn't catch your name, so please email me. Thanks.
So this discussion is to be continued at the Steve workshop. So now we have the very last talk by Chang Sheng. Yeah. Go ahead.
Thank you. So I'm Chen from UT Arlington. I formalized my title a little bit, ionosphere-thermosphere response to vibrational excited N2, especially larger than 11 inside the silent channel. This is idealized, and I'm using Gideon. So I'm going to continue the discussion like June and Brian's talk. So what I'm really doing is to examine this hypothesis like the vibrational excited N2, but in Gideon instead of using MCs. So thanks for Brian and June's talk. I don't need to go into the details of this hypothesis, but just let's do backwards is that we need the N2O continuous emission. And in that case, we need a lot of NO based on the discussions. And there's the hypothesis that if we can get the N2 new larger than 11, we probably have large amounts of NO, like shown in Brian's paper. So I put this hypothesis in Gideon. So that's some very brief introduction to our model. And this is my summation setup. I'm trying to be brief so we can have time to discuss all of this. I used a very high resolution. Usually I don't go this high, this 1/4 degrees in latitude, 1 degrees in longitude, just to resolve the fine structures of the side channel. And I impose a very strong, actually 2 channels. I trying to mimic the observations. I have a SEPS channel, and then have a inside SEPS channel, have a very strong side channel. So the maximum electric field at the center is like 100 watts per meter. So just approximately give you some sense, is 3 kilometers per second for the horizontal ion drift. And I didn't want to break anything, so I put the 3 kilometers per second. So maybe I just too conservative. We can try more in the model. And then that's our lifetime. So give you some concept, some ideas. I have a 5 minutes ramp up, then stay there for 10 minutes, then 5 minutes goes away. And on that process there, that's a meridional cut and low latitude on the left, 40 degree to 65 degree. And that's the VI east. So black dots are coming from Weimar. And if you put the strong electric field there, then you have the side channel there, like you see the red dots. Red line, and you probably couldn't see the dots. That just told you the resolution of our simulation. And I will directly jump to the NO production to show the results. On top there is our default git and run, so you will see the NO density, that's typical profile. And then, by the way, the Y is altitude, goes from 100 to 600 kilometers, and the X is the simulation time. I told you my side channel lasts for 20 minutes, but this is like 1 hour results. And this at the center, or you can imagine this is the peak of my Steve channel. That's the top default one. Then I put the flow channels inside that first, and you will see the flow channel don't do too much things in terms of the NO production besides 300 kilometers. You will see some difference there up about 300 kilometers. But what really happens or changes things a lot is you put into the vibrational excited N2 there. You see the NO density like increase dramatically. This is consistent with like the either June or Brian studies. And then for this simulation, this is like assuming I follow Brian's paper, assuming locally if you have a large speed, large real ion shift, assuming you have 5% of the N2 goes to vibrational excited. And we heard about discussion, this may be too much, like we go crazy, 5% of N2. So these things like for a modeler, we have some freedom, so I can change like, maybe we have like 0.5% and 0.05%. So this is like, I tend to give you some line plots to show you. So I hope you can see the color, you can separate the colors. So the black line on the left, that's the default one. And blue line is give you flow channels. Again, you don't see any changes below 300 kilometers. And if you put like, then you have a cyan line, magenta line, and the red line is I change the NO vibrational excited state to be 0.05% of NO density, 0.5 of that, and 5% of that. And I think you can tell, look at the peak over there near 130 or 120 kilometers, is that you change the NO new larger than 11 density by 10 times, and the maximum NO density is like increased by twice. So it's not linear. So I think what I'm trying to convey is that maybe we don't need to go that far. We don't need to be that crazy. We can still have a large amount of NO density given the mechanism, like you have the vibrational excited N2, right? So there's lots of things if you inject or put so many NO inside the channel. So I talk about the NO. I don't include the slides of the temperature, but I want to show you the plasma density or the ionosphere response here. Right, so this plot, again, is the same format as this one. So at the center of the flow channel, give you the profiles, is 1 hour results. But showing you the top is the percentage of the NO plus, and percentage of O plus, and percentage of O2 plus, then O plus is basically the plasma ion composition. And two things. The first thing you'll notice, I want your attention to the F region. You see there's everything, there's a bulge there, red peak there. Like almost everything, all the ions becomes NO plus. This is like a very classical picture. If you have fast flow, usually it's coming from the SEP study. You have fast flow, then fast flow increase the charge exchange, like change all the O plus to NO plus. And that's the reason you see there's bruising in the third panel there at F region. But I also want your attention is that looking at the bottom panel at the E region altitude, you will see the electron density increase like by almost 2 orders. And the reason behind that is you have too many NO there, and NO you have too many NO, then you have many NO plus. And I didn't show you the temperature, but the electron temperature increased there. You have the increased electron temperature, then that decreases the recombination of NO plus. And that builds up the electron density or NO plus density there, right? And we can continue the discussion, like you have so many electron density there, like your Ne increase, your sigma, your conductivity increase, and you have like strong electric field. And for sure, you will have geoheating. So I'm showing you it's the same format, but showing you the heating and the cooling from our model. It's the same thing from the center of the Steve channel. And top there is the geoheating. So just remind you, this is the subaurora. And if you don't have any significant precipitation, the conductivity there is just 2 rho. And if you look at the geoheating, it's just 2 minor. It's like 10 to the -8, between -8 and -7, something like that. That's just 2 minor compared to the geoheating in the auroral zone. But what you see, like I said, you have electron density builds up in the E region, you have strong electric field, then you see the geoheating like goes up there. But that's not my main point. And my main point is you look at the second panel, that's the chemical heating. And I want you to look at my, the text, the second bulletin. We said we need a lot of NO. We need a lot of NO coming from the reaction between NO nu larger than 11 plus O. But if you look at the right side of that equation, you produce NO, you produce N quarter S as well. And there's a very famous thing about the NO chemistry is the cannibalism reaction between N quarter S and NO. And this reaction releases chemical heating. And you have a lot of NO, you have a lot of N quarter S, and this gives you a substantial amount of heating, chemical heating there. And if you compare the magnitude, the chemical heating is much larger than the geoheating. I don't remember the exact number, but if you look at the number, look at the colors, at least chemical heating is like one order larger than the geoheating. And you have heating, you have temperature increase, you have an NO increase. You won't be surprised to see the NO cooling there at the bottom. It's immediate response to the heating and lasts like at least until 1 hour, the NO cooling is still there. It just means there's too much heating put into the system. Right, and this is, you probably like this size. And I think we're talking about the hypothesis, and I also think, agree with the Jun and Brian's talking points, is that we need the emission from observations to validate what we get the continued emission, the rates coming from our model, then you need to validate our hypothesis. So this is similar format as I show you the NO density on one of the slides. But right now, what I'm showing you is the NO2 continuum, and it's the vertical emission rates. Y-axis is the altitude, the axis is the magnitude. And in the new units of photons per, I couldn't see that, but centimeter cube, then per S, then per nanometers. So it's the vertical emission rate. And it's the same thing, you have the default one, then you put the flow channel, then you put the 0.05% of N2 to vibrational state, then increase 10 times, then increase another 10 times. So you will see the emission. But what really I want to show you, I think we can have some discussion of that. And the first thing is that if you look at the altitude, we talk about that after Brian's presentation, and you will see my peak of my NO2 continuum actually is at 100 kilometers. And in terms of the NO vibrational states, the effect, the peak is around 120 kilometers there. And I think we talk about the altitude. So right now, if you're assuming this, my idealized run is like true, or is good enough, then you can judge like at which altitude we don't really have too much NO2 continuum above, I would say, 115 kilometers there. And the reason is that if you look at the equation, if you look at how we estimate NO2 continuum, it's just at the reaction there. It's the reaction rate times NO density times the O density. And O density just decrease exponentially. So above some 200 kilometers, you won't see significant emission, even when you have large amounts of NO. And that's one, the altitude. And the other one is the magnitude. I think from what I read from the papers, I think based on, even though I have large amounts of NO, but the emission from our simulation looks a little bit weak. And to be honest, I'm not sure how much exactly how much like the emission rates we need. So I hope the observation community can give us some ideas. And then some good news. And if you compare this cyan, magenta, and the red lines, you will see there's much difference. Like you will see the large difference I show you. You increase NO new larger than 11 by 10 times, your NO density increased by twice. But if you look at the emission, you will see that one on the left is the red line. So the emission actually doesn't change that much, especially at the altitude between 120 and 180 degrees, I would say. So that means the idea we probably need to switch a little bit. The idea is it's not necessary you have like more NO, will give you more like NO2 continuum. That's not the case. And the reason is that if you go back to the chemical reaction again, and go back to how we estimate continuing emission again, it's a function of NO density and O density. And there is O inside the NO. So where does the O come from? It's come from O, not come from O2. So unless there's strong convection, either from vertical or horizontal, your NO density increase will always be accompanied by the decrease in the O density. And there's a little bit of twist there, and then if you do the calculation, your emission will not always increase with your NO density increase. I think I will stop here. That's my conclusion. And I really hope we can have some discussions. And also, we have some other discussions like the continuing in other locations like the oral zone. I hope these slides I show you, I hope I can convince you if you're using a GCM, either GITAN or TI-GCM, you have the self-calculation. At least, seems to me, it's a better option than using MCs. So if you have some mechanism or want to try or some hypothesis for the continuing at other locations like in oral zone, I'm happy to try that out inside with GITAN. Right. Thank you.
Thank you, Cheng. Questions for Cheng?
Hi, Cheng. Great talk. It's great to see this sort of thing try to be done in a GCM. That's a big challenge. I wanted to ask about the chemical heating rate.
Mm-hmm.
What kind of neutral temperature were you getting out? If you consider, like Joan and my idea of the rise time needs to be like a couple minutes. If you do a couple minutes of that chemical heating, what neutral temperature do you get, and is that even realistic?
Okay. Yeah. So I regret I didn't include the slides of my temperature profile. So I can tell you the example later, but it's like increase of few hundred K. So from 1,000 to 150, 100, 1,500, yeah, 1,500, something like that. But to your question, I don't know whether it's realistic or not, since I don't see there's any observations for us to confirm that. Yeah, that's difficult.
Any more questions? Any questions online? I think we're all needing caffeine right now. Thank you, Cheng.
Thank you.
So this is discussion time. We have 15-minute discussion time, and I'm going to pick up to something that Brian said. We need better observations. Can you elaborate what type of observations do you need? Because that's a bit open. To me, what we have right now is so complete and so much better to what we used to have that I'm curious to get your perspective on that.
Well, yeah, I mean, obviously there's been a lot of work. The one I mentioned earlier was the altitude. I think I've only seen 2 papers that have actually reported the altitude of the continuum, and that's Bill's paper, and I'm sorry, I forget the other one, but Okay, but yeah, they showed like 150 to 170 or above 130. And like I said before, I think if we could show that there's really continuum up at 200, it's not just a blip or something, that would, I think, cause us to totally rethink our theoretical approach to this. So I would love to see that, for one.
Carlos, didn't you also calculate altitude in one of your papers?
Before that, I hear people talking about the altitude of the continuum, and before I used to hear the altitude of Steve. Is there a slight difference? Close to that is the issue of, you were saying you don't see a lot of red, but sometimes Steve has a strong red component. Other times, it's not very strong. So it's like, are we talking about different things or different flavors? So starting with the first question, the altitude of the continuum versus the altitude of Steve. Perhaps the continuum is something that is observed kind of whitish and or uniform lower, but then if you have more red, for example, that had been higher, so that would be the altitude of Steve. So, I know.
So, I mean, two things come to mind. One is, it's kind of easy to get red line. Like anytime the electron temperature is above 4,000, you get brilliantly bright red line. And so it's not clear whether that's Steve or not. I think before we have to understand more theoretically of what it is before we could say whether this is Steve or that is not Steve. The other thought was, canonically the quenching altitude of red line is 150 kilometers, right? So you could have the exact same excitation going on at 140 and 160, but you get very different spectra from there. So I think, knowing the altitude of both is important, but knowing, at least from my perspective, knowing the altitude of the continuum is probably the most important.
I was just going to jump on the topic of more measurements. I think one thing that Brian and I have talked about is that it would very much help if we had IR or UV measurements to help constrain the modeling and the spectra a little bit more. So if that exists, that would be great.
This is on? Okay. So what are the ways we could measure the altitude with existing data? Like, is there any low altitude limb directed measurements that's a space I've not worked in, but I mean things where you look sideways at stuff, right? And because I think it's really hard to get the continuum. I think it's hard to get this. We have a spectrograph in Rabbit Lake and a spectrograph in Lucky Lake. And I was just asking Emma and Darren said, well, we've never seen it from Rabbit Lake because it's too far north, right? And so having two well-calibrated instruments bracketing this and having not so much else going on in the sky that you can't isolate it, right? It's challenging, but it's clearly an important observation. That doesn't help. I'm just saying, I guess I'm just saying, I don't know.
Not yet.
Oh, yeah, but anybody who wants to take it, no.
Yeah, so talking about the observations, I was just wondering, with what we have right now, can we get something like this, like the vertical emission rate? Don't have to separate different light, just give me in the units of photons. And if we can, what do we need?
I mean, the answer is no, unless you have two well-calibrated spectrographs that are looking from ideally they'd be like 100 kilometers apart, with the structure you're looking at being right between them. And I don't know anywhere in the world where there's two such instruments operating that are close enough because the thing is you need good vertical height resolution, which means they can't be too far apart, right? And you need to have them far enough apart that you have the chance of this happening,
Could that be an experiment that you could run with one of your future instruments?
Sure.
I should have asked it.
Because I'm not doing no, but that's the obvious thing is for somebody else to come with a spectrograph that they have and run it 100 kilometers south of us.
Could it be
I was going to come over here and scream at me.
No, but this is the type of thing, if we're looking for opportunities for coordination with the CEDAR community moving forward, and the idea of building something like we are with GDCG, right, that's an opportunity to be leveraged by the CEDAR community. And we could certainly support something like that, and I could easily see making a denser chain of things that could be deployed for a winter, for example. Yeah. It'll be hard to do it for forever, like, okay, now he wants it back. Please don't give away cameras.
I'm not going to give away. But the thing is, like Brian's question, I mean, there's a lot of momentum in this, you know, because Steve only sort of materialized in 2016, right? And so having all of this interest and all of this new stuff just 9 years later, there's a lot of momentum. And so what I'm saying is we have a spectrograph running in Lucky Lake. And if somebody else has a spectrograph, could they do a campaign soon? Right, so that we could create the data. I'm not saying we do the work, I'm saying they do the work, okay? Don't look at me that way.
We're about to have 8 spectrographs too.
But not this year, not next year.
Not this year, yeah.
What I'm
Correct.
saying is this momentum, somebody picked up on this decade.
Okay,
Correct.
yes. So Eric, you need to put a spectrograph south of Canada to the east.
No.
Why no?
Well, we're not putting a spectrograph anywhere anytime soon.
Because we have one in Maine. So,
but
no, you don't like that.
Could you move it?
Could you move it?
Well, it's already there, so easy if you move something.
Ours is already, like, ours is in the 51st state.
Okay.
You know?
we could ask Dawn, that's our last option.
Yeah, I mean, maybe you only need one, you know, 2 RGBs or 2 citizen science for the triangulation, and then 1 spectrograph to confirm the continuum and relate it to the, maybe that's a Band-Aid.
I mean,
Okay.
So the difficulty is that there is an optimal separation to do this, right? And then you need calibrated instruments, right? And so you want to make, I think if you're going to do this, if we're going to do this, we want to make an unambiguous observation, right? And so having, you know, like this would be, I really am saying, I mean, is there somebody, Betty Lanchester, is there somebody who has a spectrograph that's sitting in a box somewhere, right, who could mount a campaign? And it doesn't have to be it could be in Maine, like north of Maine, right? Like, you know, I'm just saying it's the obvious experiment to do. And there's, I think, only one unambiguous way to do it.
Another option is, as Brian was mentioning, if you have citizen scientists' observations, as we had in one paper with citizen scientists and a camera, we were able to determine the bulk height. That's the thing. We didn't get spectral resolution or any kind of information.
But I mean, the challenge is that, right? That's the challenge. Right?
But before that, the challenge is to say, okay, we're observing this structure, Steve, with a lot of red, with pure continuum at 150 or 250 kilometers, or 200. I think if we start with that, then we can get into more specificities like spectra.
So Emma is pointing at me because, so should I talk about Arctic Smile?
Yes, I think you should.
So Emma, being brilliant Emma, realized that the citizen scientists have been adapting their data to something that is similar to what we do. But we are not doing the other side, changing a little bit our field of views and the way we take data to be similar to what the data they take. So right now, Emma has a special campaign running where at Lucky Lake, so for those of you that are not familiar, at Lucky Lake there is a beautiful RGB all-sky imager. There is also the spectrograph. And right now, the University of Calgary has 2 cameras, one looking east and one looking west. So for example, for things like Steve, we could look sideways and calculate altitude.
Non-all sky, so like a photographic lens, looking sideways, taking systematic observations at the exact same cadence as the science measurements, but looking sideways. So in theory, if we were to see Steve, for example, in the all-sky camera, we can locate it with the sky map, right, in terms of where it is relative to the site, and then we would have on-side or on-end observations towards it where we could look at the altitude.
You won't be able to get the altitude.
Why not?
Well, I mean, because you're looking east and west. When you're looking along the arc.
Right, but we'll have the.
It's like the worst geometry for the altitude. No, I mean, so the thing is, let's just argue, you know.
Let's do this.
So, this is fun. So the ideal thing, I mean, from my perspective, the ideal thing is you sit 100 kilometers apart or 80 kilometers apart, one camera looking north, one camera looking south, right, along the same meridian, you know, and with the dense array experiment, but with some better spectral information.
If we're just talking about getting the height.
Yeah, but this is what you need to get the height. You can't look along an arc and get the height.
We're pointing north. Oh, John's on my side. Here, John.
This is the, I guess this is the end of my career in Calgary, right? You know,
yeah.
I don't understand how one could get a height looking along an elongated structure.
But we're not looking necessarily along it.
That's
because
right.
We're looking north,
there's an offset.
west, and northeast. Remember, we're bracketing north.
Yes, but how do you get the height? You don't know where it is. You don't know where it is. You haven't got it georeferenced unless you look at it from two locations.
Eric, it seems that Emma is not being clear enough. You're not seeing west and east. You're seeing northwest and northeast.
Yes, but,
so you have the component.
But my point is to say the height of something with, this is Sturmer's experiment, right? I mean, you have to look across the thing from two sides of it. Otherwise, you don't know where it is positionally, horizontally.
Because you're seeing from the same place.
Yes.
Okay, I get
Yes,
it.
I mean,
Yes.
it is not the way to do the measurement.
Yep.
Right, like.
Okay.
So we need
relative.
We need one more camera. 100 kilometers south of Lucky Lake, or 100 kilometers north of Lucky Lake.
We have that. We can have that.
Yeah, that's what we need. And ideally, a spectrograph, 100 kilometers north or 100 kilometers south.
I can't give you that.
No, but somebody else might have one.
Yeah.
But I think, but again, like for the community, I mean.
No, but there's something, sorry.
The triangulation has to be done looking across the structure from two different directions.
Yep.
There's no other way to do this.
Until then, we can use current observations. We have a case, we're working on that case, November 4th, 2021, a bunch of observations from citizen scientists in New Zealand. We have our all-sky camera, Mount John. Separation was less than 100 kilometers. I think it was 70 or 60 kilometers.
But no, I mean, 70 or 80 or 100 is fine, yeah.
And we were doing exactly what you're saying. With Mount John, we were looking, well, it's all sky, so you can look the eastern part. And then we have pictures from citizen scientists that look what's east, zenith, and west.
Right.
And we took those frames, and east and west, and we calculate the height without the calibration or anything specific. The result we got was, yes, there is a nice height, but interestingly, east and west heights were different. So for the first time, it's like, wow, we have an arc that is not the same height, altitude. So that's something that can be done with current observations. It's a question of finding the geometry and the storm and contacting the citizen scientists, and we can do it. In the meantime, yes, we need to work on what you're suggesting.
Pardon me?
Could I add a little Can I add a little comment to the triangulation debate? If you have a camera anywhere and you see something in your field of view, that defines a ray in three-dimensional space that heads out indefinitely. If you can identify that you're looking unambiguously at the same thing from anywhere else that's separated, you'll have another ray, and where they intersect, that tells you where it is. And it doesn't matter whether you're looking from north, south, east, or west. If you have two rays that are not parallel, but the trick is you have to know you're looking at the same thing. And so if there's enough modulation or local structure for you to do that, then it doesn't matter. But if it's a long, diffuse target, then you have a problem.
Right, and the whole thing is like, so Pekka Janhunen had gone so far in, like, back around 2000, 2002, he wrote a paper where he was inferring heights from one imager, right? But he had to pick an altitude for the bottom of the arc. And then once you do that, well, I mean, if you're off by 2 or 3 kilometers, everything else is off, right? And so, and you're right, if you're looking east and west, right? But the problem is these are rather diffuse, elongated structures. That's my only point is that it will work best if you're looking across it. I'm not disagreeing with you. I just, you know.
If there's a latching point, if you're looking up, there's a latching point of the green aurora.
Can I show a picture?
Yes.
Can anyone see this?
No.
No. Wait.
Okay, I'm trying to screen share.
Wait, I think they need to help us in the room. And I know we are closer to the coffee break. But
Yeah, it can just be really rapid, but this is from the paper with the missions. And then one of our events, we have this like an image from a citizen scientist and an image from an all-sky taken at basically the same time, showing a vertically extended continuum. And we also have kind of continuum like pillars in the same event. Now we're seeing it. So you're seeing it?
Yes.
So, yeah, so, I mean, from this data that we have, we were like, okay, it's quite vertically extended. And this is another reason why we're like, maybe NO is another challenge, because how would it get this vertical extent? If this, you know, this is a tall, like you can see in this citizen science image in the middle, like this is kind of a vertical structure. And it's clearly pretty large. So I just thought that would, if you want to look at this event, it's in our paper on like ghost, first observations of ghost stuff.
Can I ask, that's, the one end of that structure looks like it's right at zenith.
Yeah.
And so that means that I'm trying to think, does that mean, can you get the top of that, the altitude of the top of that structure from that single measurement because you know where the field line's going?
I'm not sure.
Because that's just following a field line, right?
Yeah, but I mean, how do you know where it starts? Like you were saying, how do you know where?
It starts where, oh, yeah. Okay.
But I mean, it's clearly quite vertically extended. And in C, panel C, you can see there's like, you know, it's also, you know, tall rays. So, I mean, it's hard to put numbers on this, but it seems like maybe 200 kilometers wouldn't be too difficult. I don't know.
This is great discussion. Thank you, Rowan, but I don't want to go over time. I'm going to stop it here, but I'm taking notes of the things that we need to keep talking during the STEVE workshop. I want to thank all the speakers, but special thanks to Rowan, to Vincent, and especially to Josh, who's an undergrad and presenting our session. Thank you so much, everyone.
Thank you, guys.